I'm just going to do a quick introduction. My name is Steven Rosell. I'm a technical specialist with Autodesk, focusing on Maya. And we're actually sponsoring this session, so I just want to say a few quick words. I'm not going to take up a lot of time, though. Mainly just an introduction. So today, the presentation obviously is by the guys from Guerrilla Games. And Marijn, is that right? Did I get it right? That's right. So Marijn, and I'm going to butcher your last name, I'm sure. Gijsberts? Did I get close? Yeah, that's okay. Close enough. And Paula Spanning are two artists from Guerrilla Games. Marijn is the lead effects artist, and Paulus is the lead tech artist. And they're also, I just wanted to point out, doing a presentation at our booth, at the Autodesk booth at 4 o'clock. If you want to check that out as well. The Autodesk booth is at number 1432 in the North Hall. So if you like the stuff they're talking about here, come by and check it out at our booth as well. But without further ado, I'll turn it over to them. Thanks. Oh, and also, I'll stick around at the end if anybody has any kind of more Maya-specific, like product questions or Motion Builder, Mudbox, anything Autodesk-specific. I'll stick around for Q&A at the end. So, thanks.
Thank you. So yeah, as the introduction said, I'm Paulus Banning. Before we get into the making of Killzone 3, we always like to start off with a little bit of background info on who we are and what we've done. So we're Guerrilla Games, founded in 1999, and since 2005 we've been part of Sony Computer Entertainment. And that means we've been sort of creating games for over a decade now. More precisely, in our case, we've been creating one game for over a decade now. And that is the Killzone franchise. And for those of you who don't know it, as you can see from our cover art, it's basically about shooting red-eyed space Nazis. In this time, we've seen 3 generations of console arrive on the market. And before we get into the real presentation, I always like to show you a little bit of sort of how much the industry and the quality of the games has changed in that time. The following is a small snippet from a demo video that we created in 1999 when we were trying to sell the Killzone game to Sony. And actually, at that time, it wasn't even called Killzone yet. And about 12 years later, the 3rd installment of Killzone looked like this.
I know what this nation needs. I will give you justice. Tomorrow we launch the greatest military campaign in our history. The ISA forces are in disarray. Within 3 hours, my forces will overwhelm them.
They're gonna find us. It's just a matter of time. Gotta keep moving.
General, the Higgs are knocking at our door.
All hostilities will cease immediately. Stand down and surrender.
I didn't come here to run from the Hellgas. Order the attack, you coward!
Our priority is the lives of my men.
We've all seen what the Hellgas do to their prisoners. Where are we going? To finish what we started.
Where are the ISA? Why haven't you delivered your weapon prototype to the military? I will not place weapons of such magnitude into the hands of a total incompetent. This is an outrage!
Always fun to see how far we've come as an industry, I find it. So what will we be talking about today? First of all, I will start talking about some of the tools and techniques that we've used to create the environments and levels that you see in Killzone 3. And after that, I'll focus a bit more on some lower level technology as I'll explain how we embedded our own render engine into the Maya viewport. Then our lead effects artist, Marijn, will talk to you about how artists use the Maya hypershade to construct the shaders that you see in our games. And particles are up next, as Marijn will explain how we combine the hypershade's power with our in-house particle tool to create a very flexible visual effects pipeline. And finally, he will show you how our lighting team used the renderer in Maya's viewport to create all the lighting for both the game and the cinematics. So environments first. For us, the main ingredient for building our environments is a concept that we call building blocks. And building blocks, as illustrated here, kind of function like Lego blocks, in that they're very generic, reusable objects that our artists can use and combine in many different ways to come up with basically any type of environment that we want. These things can be anything from really small objects like pillars or railings or pipes, but also complete buildings or vehicles, really depending on the requirements of the environment that they're building. These specific requirements are first derived from mood boards that are created by our visual design department. Here you see one of those mood boards on the right. What happens, these are handed over to our environment artists, and they will basically start dissecting the whole image and identifying the individual parts that it will need to recreate it as a game environment. These individual objects are then sent back to our visual design department, and they will start speccing out the designs for the individual building blocks. Here's another one of those mood boards. This is one from our jungle level, and I put this in the presentation to illustrate that even an organic environment like this is still mostly constructed from these building blocks. What you see here is one of the briefs, so that's what comes back from our visual design department, and actually these usually don't go back to our environment artists, but straight to our outsourcing partners. As you can see, there's multiple, multiple objects in here as we design these things in families, not in individuals. And the idea is that every building block in a family shares the same shader and shares the same texture set. On the left, you see a bar where we include additional information, things like maximum triangle counts, UV set, maximum texture sizes, all that stuff. So what you see here is sort of a single package that we can send out to our vendors, and we know exactly what we're going to get back. And we send out hundreds or even thousands of these for a game like Killzone 3. So once we get the building blocks back, we get sort of 3 standard components in there. There's always a high resolution mesh, there is a low resolution mesh, and finally we have a physics collision mesh. And what you see here is basically a different building block from the same family, and you see it has the same 3 components. So it's a very predictable asset for our pipeline. What we then do is we export these components through a custom tool set, and that will create the final building block asset. And this asset can best be seen as sort of a data container that will carry the building blocks data all through our pipeline. And from here on out, we'll only use the building blocks in this form. So the original geometry that we got back from the outsourced vendors will generally not be touched anymore. The same export process also puts the building block into our asset manager, and this will be the starting point for our environment artists to find appropriate building blocks they need for their level, and then instance them into the Maya scene. And that's what you see here. This instancing is done through a custom Maya node that we have, and it will show a representation of the geometry, but it will not be showing Maya geometry. This is actual live game geometry that you see here. And what they start doing is by manipulating, copying, duplicating, what have you not, they'll start building up the environments. They're free to move, rotate, scale, whatever they want to do with it, and combine various building blocks from the same style to get to an environment or part of the environment like you see on the right here. Once that's done, we export this, and from that point on, the environment geometry can be loaded into the game. And there's a couple of great advantages that this environment pipeline gives us. For one, there's automatic updates. Since from the very early stages on, we only instance these objects into the game, if we have to make changes to them, like optimization or art directional changes, we only update the source building block and the whole game will update itself. For that reason, it's also very memory efficient, because we store only one instance of each building block in memory and then instantiate it throughout the game. And finally, since all our environments, like all of our other content, go through a conversion process before the game is actually started, this step allows us to insert some really useful automatic data processing. And one of these types of processing that we do, I mean, there's many, but there's a few that I'd like to point out specifically, is we take all the physics meshes of all the individual building blocks and we collapse them into one big mesh. And that's simply because our physics engine is much more efficient at dealing with single large meshes than a lot of individual small meshes. Again, because of that conversion process, if we then make a change to one of the source physics meshes, these collapsed meshes will be updated automatically. And like our physics engine, our render engine also much rather gets large single objects than a lot of individual meshes. And we try to collapse these as much as we can during the conversion process as well. And this is the part where our work with various levels of details come in. What we do is we use a conversion process to create what we call nested LODs. I'm hoping everybody here knows that LOD in this case stands for level of detail. An LOD group is basically a group of meshes that switch visibility based on their distance from the camera. And for us, a nested LOD group is basically a lot group within a lot group. So the idea is that when you're close, you will see the individual building blocks, the individual instances, with their own individual level of detail setup. But when you're sufficiently far away, we just replace the whole group and put one single collapsed mesh in their place. And I want to try to illustrate this setup as best as I can. So what you see here is sort of a representation of a group of building blocks and the camera being sort of 5 meters away from the whole group. And you'll then see all the individual building blocks in their high resolution state, which I've illustrated by showing you the bounding boxes so you can see they're all separate objects. We then move the camera to about 20 meters, and you can see that the building blocks on the right have now swapped to their low resolution version. That's just to reduce the amount of polygons that we have to render. But if we look at the bounding boxes, they're still all individual objects, so we haven't been able to optimize anything there. We now move the camera much further away, 50 meters in this case. All building blocks have switched their low resolution state. And in this case, it's much more efficient to just replace the whole collection with a single mesh. Also because in general, in game levels, you're close to these things for a relatively short amount of time, but there's always building blocks in the distance, and you want to get them as fast as possible. So what we've done here, as you can see, looking at the bounding box now, it actually is a single mesh. And that single mesh, again, has been generated during the conversion process. So just like with the physics meshes, any changes to the source mesh will automatically propagate once you restart the game. And here you see a screenshot of the same collection of building blocks as it appeared in the game. So that's it for the building blocks. I'd now like to follow up with showing you 2 tools that we use in our environment pipeline. This is the level editor, and the level editor basically allows us to edit multiple Maya files in a single session at the same time. We got a need for that based on how we work with Killzone 2, is that we separate a lot of our data over various files, so lots of people can work on the level together. But there's always content in various files that's dependent on each other. An example of this would be lean and peak cover points that are dependent on the geometry around it. And in Killzone 2, basically, if they move the geometry, then I have to open the other file and move the cover points, et cetera, et cetera. Very nasty workflow. So this tool basically allows them to work on everything at the same time. What you see here on the right tab is what you saw there on the right tab, my bad, is the current outliner, custom outliner that we put in. And that will only show you the content of the actively selected Maya file. The middle tab here is where they choose the Maya files they want to load and also the way they want to load it. And once again here, there's 2 files loaded, 2 different outliners. The way we've done that is that we've added a custom node to the Maya scene. Here we're loading in a 3rd file, by the way. And whenever we load a file, we import the whole contents of that file underneath that custom node. And when we save the layer, as we would call it, there you see the custom nodes. As we save the layer, we basically do a selection of everything underneath and export that to the original Maya file. And the way that's set up is just by a very large collection of callbacks that we've added in. These callbacks make sure that any nodes created, duplicated, edited, or done whatever with them stay within their respective layers. Because since these layers represent various Maya files, it's very dangerous to have nodes swap to a different layer because people actually lose them from their original file. Also added in some additional functionality that if you have a layer open and you close the level editor, it will automatically swap back to that layer as a single Maya file. What you see here is they're able to save these setups, so when you get back in the morning, you can restore your setup. It will load all the files in their original configuration. There's a couple of ways that we can load them. We can load them for edit, in which case we'll actually import the geometry and mark the file editable, but we also have various ways of referencing in the data if you just need to look at it. These are the options you have when you close level editor. So in this case, the user has chosen to keep the layer open, and that will basically replace the current scene with the actual Maya file. As you can see now, we have a normal outliner back. It's basically back to normal. And if the user now starts the level editor here, it will actually recognize the fact that you have what it knows as a layer opened, and will allow you to basically now open it as an actual level editor layer, and the custom outliner is back. This tool has significantly increased the speed with which we can edit our levels. And both our environment artists use it quite a lot, but also our level designers really liked it. And actually that was the reason why we named it level editor. It's a bit of a weird name for what it is, but our level designers were always screaming that we didn't have an actual level editor, so we figured if we just name it like this, they can shut up. The next tool is our live connection between Maya and the game, called Game Link, and the video's not that fast. And this allows us to link operations in Maya and the game. The first thing we did is link the cameras. So you can move the camera in Maya and it will move the camera in the game, but also do it vice versa, which is very useful for finding bugs when you just have a screenshot and you need to find a location in Maya. We can move and manipulate lights in this. Lighting artists use it, and we can move other objects around and also annoy the AI immensely with this. It's one of those tools that we added in as sort of a framework, and we didn't initially really have a large plan of what we wanted to do with it. And it turned out that, for some reason, our sound designers really like to be able to link the cameras up, where we thought our environment artists were really going to use it. So it just goes to show you never know who likes your tools best. So now for the bit more technical part of the presentation, and I wanted to talk about a big customization that we did to Maya, which was adding our own render engine, viewport renderer. What you see here is a scene from one of the cinematics in Killzone 3. This is just the flat shaded view. Basically a bit of history that when we moved to the PlayStation 3, we figured that the new shader possibilities that we had is something we wanted to put in the hands of the artists and not in the hands of the coders. So we created a custom hardware shader node, which would allow our artists to author the shaders in Maya and see actual representation of what they would look in the game. And Marijn will later talk a lot more in detail about this shader setup. I just put in this video to show you the difference with the next one. And this is the same shot, but now with our custom hardware shaders applied to the geometry. This is our forward render being used, so we're still only rendering the shaders. We're not rendering the viewport itself. And there's then also a lot of things that are missing here compared to the actual game. We have a lot less lights that the shaders will pick up. And there's a lot of viewport or screen space operations, that we do, like post-processing, that you'll never be able to see here. We already had this when we were doing Killzone 2, and it was a huge benefit, but we always felt there was something missing. We had this great render engine, and what if we could get it in Maya? So that's what we did. And this is the same cinematic, and now we've taken over the complete viewport. And what you see here is the actual game renderer. It will look exactly the same in the game. We get all the lights that our engine support, which is basically an infinite amount. And we get things like post-processing and color corrections. It's a bit subtle, but you can see there's some bloom happening on the guy's shoulders. And we can only do that when we take over the full viewport. So how do we do this? And this is the in-depth part of the presentation. There'll be more fancy videos after this. What we did first is we created sort of our own custom world in the Maya plugin. And in that world, we'll be able to store, access, and manage all the geometry and lighting data that our engine would need to render it. This is called the Maya Core World. Basically, Core is the name of our engine, so that's where it came from. And this Maya Core World contains the following items. There is a custom scene graph where we store all the data that our engine will need to render the view. This data comes in the form of geometry objects. This is the objects that represent the mesh data that we need to render. We have a callback manager. And this callback manager is basically responsible for keeping the custom scene graph completely in sync with Maya's own scene graph. And then obviously there's the viewport render that generates the final frame. So this geometry object that I mentioned, what does it do? It's basically a wrapper for Maya's own vertex arrays. So rather than copying all the geometry data into our own setup, into our own world, we're basically just storing a pointer to the original Maya geometry. It gives us a couple of benefits. One, obviously much less memory intensive, but it also means that deformations like skinning or other types of deformations are automatically picked up because we just refer to the original Maya mesh. It also gets all the draw flags from the Maya mesh. And finally, these geometry objects are added to our custom scene graph whenever we assign a shader with our custom nodes inserted into it. So that's sort of the trigger that will add or remove it from our graph is whether the shader is connected or not. The callback manager, as I said, it's responsible for keeping both worlds sort of in sync. We have a number of callbacks that we have in here. The first one is obviously a callback on adding and removing of nodes in Maya. We obviously need that to know when new stuff gets added to the scene so we can check if we need to add it to our own scene graph. There is the callback for intercepting connections between nodes. As I mentioned, assigning a shader, basically making a connection between a shader and a piece of geometry, can be the thing that triggers the addition of that object to our scene graph and removing the same. And a couple of things that we found out with this callback manager when we were implementing it is that Maya continuously triggers callbacks when you're opening or importing files. And this is a bit dangerous if you immediately start working and trying to set up a sync between Maya's graph and your own graph, because Maya's graph is still changing quite a bit. So one of the mistakes that we initially made is not picking this up, and we learned the hard way that you need to definitely wait for Maya to be done with its own file I/O operations before you start doing anything yourself. The other thing is that with nodes, you can obviously add callbacks to the constructors of the nodes. The problem that we found with that is that once a node gets deleted, you can put a callback on that and it can remove itself from the core scene graph. But if you then do an undo operation in Maya, it will not actually repeat the call to the constructor, so the callbacks will not be called. And that's the main operation and why we built this separate callback manager. So we're separate from all the nodes in Maya itself. We're just getting a grand overview of the scene and try to replicate that. Last bit before we get to the video again is the viewport render. And this is basically where we collect all the content in our scene graph that we need to render. We then call the deferred render commands to render the various deferred buffers. And then there's a post-process pass that we combine all these inside the Maya render context, and then the result get put in Maya's own frame buffer. And finally, to be able to display all the Maya HUD elements and things like manipulators and lights, etc., over our own render view, we had Autodesk implement a feature that would allow us to call the normal Maya render after we were done rendering the view and mask out the items that we still wanted to see. And this is something that came in a bit later, but it was definitely the finishing touch on our custom render view, because now the artists were not only able to see the results that are seen in our engine, but actually manipulate it. And that's something that you can see in this video here. It's the same scene as we saw before. Excuse me. So here we go to the shaded version. As you can see, it's still the same scene, and we're just rendering the shaders now. The lighting is a bit coarse, and we were not able to pick up all the lights. I think there's a maximum of 4 or 5 lights in this case. But interactivity is still quite nice. Now we will switch to our deferred, and now we've taken over the complete viewport. But you can see the lights are still there, the manipulators are still there. They're still rendered by Maya on top of our own rendered image. You can see the lighting is a lot more subtle. And this is, again, it's our own viewport render. There's no distinction between this and what we see if we would run the game on a PC, for example. I think Marijn will talk a bit more about this, but this is kind of the workflow that our lighting artist had when we were trying to light the cinematics, all 72 minutes of them in about a week, I think. We also have, I should be looking at that now, yes, our own deferred render globals. So here you can see we also, the same colorization and post-processing options that we have in our engine in-game, we have in Maya. You can see we're using colorizing here with depth settings. This is very nice. This is our debug views. These are actually, they came for free because we had them in our game anyway. So these are all the various buffers that our deferred renders out. So this, for example, the normal buffer. Turned out to be very useful to debug shaders and objects to see if there's something wrong with your normal maps, for example. You can get a full view of the thing. Let's see, then here's our lighting buffer. There's a lighting pass. If you specifically want to look at the influence of lights on the final image, we can turn on this buffer. And those are actually the two main use. We've at some point had our engine coders put in additional buffers. But the fact that you can get this kind of in-depth information about what's rendering in your scene and how your shaders and objects are being rendered is very, very useful. That's it for me. I'm now going to pass over to Marijn, who's going to talk about game shading, particles, and lighting.
So, hi, my name is Marijn Giesbert. I am the lead effects at Guerrilla Games. And today I'll be showing you how we created some of the shaders in Killzone 3 using Maya's Hypershade. And I'll go into detail on some of the techniques that we used in constructing them. So after that, I'll show you our particle editor, and I'll end the presentation by explaining how we use Maya to help light our game. But just before we take a look at all of that, I want to quickly show you some of the differences between Killzone 2 and Killzone 3. So when we started working on Killzone 3, we decided that we wanted the world to be a lot bigger than on Killzone 2. And just to illustrate how much bigger it has become, let's take a look at the following videos. So what you see here is the first level from Killzone 2. I think it's called Corinth River. And then when we zoom out a bit further, next to this you'll see a level from Killzone 3. And as you can see, it's quite a lot larger than the Killzone 2 level. But it wasn't just the scale that went up on Killzone 3, it was also the amount of detail and variety that we added to our environments. So what you see here is a Killzone 2 multiplayer map, and for Killzone 3 we did a remake of this level with a different theme, which looks like this. And as you can see, the amount of detail has increased quite a lot. The geometry detailing, the detail in the shaders and the lighting have all gone up in quality. So now let's move on to our shading process. So as Paulus mentioned already, we have the option of running our engine in the Maya viewport. Besides using it as an editor for constructing levels, we also use Maya's Hypershade to define all the materials in our game. As you might notice from looking at the Hypershade, you can already see that we use a lot of the existing Maya nodes. So we're using multiplies, the set ranges, the layer textures, file nodes, sample infos, etc. And we combine these with some custom nodes that our engine supports, and that's for things like vertex coloring, depth distance reading, normal mapping, etc. One of the what I think is the most enjoyable part of working on shaders is the instant feedback that you get in the viewport while you're tweaking values and trying out lots of different things. When we're done, we save our shaders in the Maya scene, and we export these to our engine's core text file format, and then they're added to our asset manager's database. So here you can see our asset manager in action. Besides using this tool to browse and load in building blocks, props, or level design objects, as Paulus already mentioned, we also use this to load in shaders on objects. So when we assign one of the exported shaders to our level geometry, it loads in the shader as a Maya reference object. And if a change to a shader is made, we re-export the file. Our build machines recognize the content change, and they reconvert and cache all the content containing that shader. So next, we'll take a look at some of the terrain shaders that we did. So here are some examples of the terrain shaders in Killzone 3. You can see the nice transitions between the different types of materials and the amount of detail that we added. And for most of these shaders, we blend in multiple textures at the same time using specific reveal masks for each texture transition. Now, these reveal masks play a very big role in achieving these sort of results. Now, I will take you through a typical shading network of one of these shaders and show you how these have been set up. So, here you can see the vertex colors that are painted to change the appearance of the surface. So the black vertex colors are painted to add more damage to the surface, and we're using white to remove the damage. So what you see here is the network that's created the shader, and it consists of the following textures. So we're using these three color maps, and these are the normal maps of those textures. And finally, we created 3 masks for defining the damage reveal pattern. Now, the color and normal maps, we layer them using Maya's layer texture node. And we've ordered the layers from top to bottom. The layers are blended through an alpha that we get using these 3 images. So for now, let's get rid of the color and normal maps and take a closer look at these mask textures. Now, as you will notice, we have given the 3 masks varying color ranges. And the reason for doing this is so we can already establish the reveal order importance. And it's also, in that way, we save using a set range node. Wider values are used to do most of the initial breaking pattern on the surface. We're using the gray values for the more secondary chunk defining detailing. And the black values reveal more of the smaller details, which are probably very hard to see on the screen. So by setting it up like this, we're in a way giving depth to our masks. And in the shading network, we subtract the masks from the vertex colors and route these through a set range. Now, the results of the masks for each channel at that point looked like this. So the right image, that shows you what the painted vertex colors look like in that stage. Now, getting the proper values for the set range usually takes quite a bit of tweaking, but in the end, it gives some really nice results. And this is really the node that helps us define the depth for our masks. So now that we defined our reveal masks, we can apply them to the layer texture. So in the layer texture node, what we do is we multiply a dark color with the blue mask we get from the set range. Now, most of the different blend modes in the layer texture node are supported by our engine, so we can add, subtract, or illuminate textures. On top of this layer, we layer the cracked wall using the red mask. And finally, on top, we add the undamaged wall using the green mask. And after that, we apply the same principles to our normal maps, and those results look like this. And this final video will show you how the vertex painting is affecting all layers at the same time. So now the big advantage of using this masking technique compared to using each vertex color channel, so the red, green, and blue for blending, is that it's a lot more intuitive for artists to work with. So next, we'll take a look at how we're able to access our engine's buffer data to create an outline effect around objects. So in this video, you can see the little display at the bottom of the screen. And it displays the objects in the world with an offset, and you get a sort of outline effect. It might be a bit hard to see from the... And this is another video. It's quite hard to see here, but it shows you you're infiltrating a Helgas weapon facility and you're wearing a Helgas mask. And there's little interlacing outlines at the edges of the screen. And although these are probably not the most exciting examples, I still like to take a look at how this was achieved, since it really shows the cool stuff that we can do with deferred rendering. And the examples will be a lot clearer than this, hopefully. So the first thing we'll look at is the setup of the interface elements that you just saw. And these are rigged to, and they're only visible in the first-person camera. Now, a reason why we're using all these separate HUD element objects is to add a sense of depth, and this was especially noticeable when you play the game in 3D. The vignetted plane you see in the foreground is also constrained to the first-person camera, and that contains the shader that's responsible for the Helgas vision. So let's take a closer look at that network. So this is the network, and in the corner part of the graph, you'll notice these 3 purple nodes with a griddle logo. And these are the G-buffer nodes. And these nodes allow us to read from a specific deferred buffer, and then we can use the data from that buffer to create our shaders. So I'll show you some examples of what data we can read from the G-buffers. So we can read the normal data. Here you can see the albedo buffer. This is just the pure color texture data. This is the specular buffer. And this is the depth buffer data. And this is actually the particular buffer that we use to create an outline effect. So what we did is, you see that little node there? It reads the depth buffer, and it offsets it in UV screen space by 2 pixels in the positive X and Y direction. And then we read the buffer again, but this time without the offset. It's over there. And then we subtract the 2 from each other. And that leads to the following result. Again, this is very hard to see on there, but there's like a little outline visible. We then repeat the same process with these nodes, but this time we offset in the negative X and Y direction. And again, we subtract the non-offset data. And that leads to this result. Before we subtract the buffers, they're routed through this clamp node that you see over here. And we do this to restrict the depth distance that's being read to 200 meters. Now, as a final step, we use these nodes over here to boost up values of the subtracted depth buffers, and then add the results to accomplish the image you see here. Now I'm going to run a video, which hopefully will show it a bit better. There's also some really nice subtle lines in there, but it's also hard to see from here. So the remaining part of the network that is used to create the interlacing and color and vignette effect. And although we haven't made a lot of use of the G-buffer reading on Killzone 3, it's a node that has a lot of potential cool stuff you could do with it. So in a moment, we'll take a look at our particle editor and how we set up some of the shaders for our particles. But just before we do that, I want to take a look at a clip of a cutscene, which is quite effects heavy. So in the next video, you can see the effect for this explosion loaded in our particle editor. So again, one of the nicest things about working on video games is the instant feedback that you get while tweaking values, and this really speeds up the process significantly. So our particle editor pretty much has all of the basic features that you'd expect from a particle editor. So we can set values for particle lifetime, the particle size, the emission rates, rotation. It's pretty much all the basic stuff you expect from a particle editor. Now let's take a closer look at some of the elements of this explosion. So for this particular effect, we've used about 30 particle systems, and we spawn about 2,500 particles. This particular effect was made for a cutscene, and the nice thing about working on cutscenes like these is that we can really push our particle systems much further if needed. We don't have as much performance restrictions as we do with effects for gameplay, and that's because all of our cutscenes are rendered out to movies. So here's some other features for our particle editor. One of the new features that we got on Killzone 3, which we were really happy with, was the option of polygon trails. So these really helped in getting much more continuous missile and dust trails. And again, this is, well, you can see it. It's, since we're using the deferred rendering, we can spawn lots of small lights with our particles without any, well, significant performance drop. And mesh spawning is also a possibility. So yeah, these are just some of our particle editor's features. Now, adjusting the emitter settings on a particle effect is actually only half of the work in creating effects. The other half lies in the creation of the shaders. And like I've just shown you, we use Maya for that. So it's pretty much the same process as building any other shader. The main difference in networks is that we usually define a bunch of variables that help us tweak the shader from inside our particle editor. So one of the basic variables that we use on pretty much every particle effect is a z-feather value, and this lets us fade out our particles when they get closer to objects. And another one we always use is the color value, which allows us to do overrides on colors of existing particle textures. So let's take a look at the tweaking of some of the variables. So the next example shows you the result of the shader we just saw applied on a particle system. For this effect, we only made about 10 particles, and the shader makes use of a really nice flow map technique, and you can find more on this in a paper called Water Flow in Portal 2, and I can really recommend yeah, looking into that. The variables that we've tweaked for this shader are for UV distortion amount and UV scrolling speed. So here you can see the left example has a bit of UV distortion. And the middle effect, we actually removed all of the UV distortion. And on the right effect, we've increased the UV scrolling speed. With the color value variable, we can do overrides over the colors. We do this by multiplying the vertex colors and alpha with the source file textures. And you can see the little bars here that represent the particle lifetime, and you can see how changes affect the particle's color over time. Now, before ending this part about the particle editor, I want to show you one more video of a short experiment that we did, but never ended up using it in the game. So the goal of this experiment was to see if we could use our particle system to generate large-scale background battlefields. And we really tried pushing our particle systems to their limit. So in this video, all the tracers, explosions, and even the characters that you see walking are particles. And in the top right video, you can see a close-up of the battlefield. Eventually, we decided not to use it in the game because of the lack of quality. Well, hopefully this short demonstration gives you a bit of an overview of what we can do with our particle systems. So now the last subject I'll be talking about is lighting and how we use Maya for this. So this video will show you some of the different passes of our lighting process. Now, Killzone has always been known for its lighting. The primary reason for this is that we put a lot of effort in getting the ambient values interesting. So to enable us to do that, we have always used Maya in combination with cutting-edge rendering technology. So for Killzone 1, we used Mental Ray. On Killzone 2 and Liberation, that's our PSP title, we used Turtle. And for Killzone 3, we're using Sony's internal lighting solution. We always try to get the maximum amount of details in our shadows and transition areas of the lighting, meaning that we work with hundreds of fill lights and ghost lights to get gradients in the flat shadow areas, to break up the evenness in the lighting. And we really like, in a way, to paint with light. In the end, we baked the solution out to non-directional light maps for our static geometry, so that's the building blocks, BSP, and we use spherical harmonics data for our dynamic geometry, so all the characters, vehicles, and dynamic objects in the world. Spherical harmonic data is sampled from a point cloud-like data structure that we generate based on waypoints and the geometry. And this point cloud is not very dense since we're limited to 2100 light probes on the PS3. But sufficient enough to get all the intricate lighting that exists in our light maps to be visible on our dynamic geometry as well. While we make this ambient lighting, we are also placing real-time lights to give punch to our lighting. But just looking at our levels with the light maps and spherical harmonics data, it already looks quite nice, actually. So this video shows you the process of lighting a shot from one of our cutscenes in Maya. In total, we had about 72 minutes of cutscenes. And all of the effects and lighting on these was done in the last couple of months of the project. I think it was actually, we had about 2 months to do all of that, while also finishing the game. As we've told you, our game engine is a deferred renderer, which gives us more flexibility and speed during lighting than a traditional gaming engine. But an even bigger advantage is that it runs directly in the Maya viewport. This really allows us to add, copy, and tweak the lighting of the scenes in real time. Now, the system only supports directional, omni, and spotlights. Well, we actually had little need for more advanced lights. Also, as the system didn't support any real-time radiosity or radiance, we had to use secondary omni lights to create the illusion of bounced light. The nice thing is that we can go pretty nuts with the amount of lights that we use in the scene. As the system performance is mostly dependent on how many lights you have per pixel. That means you can have hundreds of lights in your scene while still remaining interactive. And I think that already brings us to the end of this presentation.